Okay, so uh, an alpha particle, okay, mass for u, uh, charged with positive 2e, means that it has a positive charge. It's a positive charge particle, it's not a negative charge. Enters a magnetic field with B 1 Tesla with a speed of 7 times 10 power 6 meter per second, perpendicular to the magnetic field. So sketch a label diagram. Sketch a label diagram uh, to show the direction of the magnetic field and the path of the alpha particle. Okay, so number one, we have to show a path. So let's say we have here the B is pointing into the screen. The magnetic field is pointing to the screen over here. Okay, and then we have alpha particles that enter alpha particle, positive Q, 2Q, enters the region of the magnetic field. So what happen is will be deflected by magnetic field force. So it will be deflected in uh, the force of the magnetic field. The force magnetic field will be going to the left side. Okay, to the left. F going to the left. You can check with your uh, left hand rule, left hand grip. So uh, your index finger pointing to the screen, and the Q, the velocity of the Q is pointing up. So force your thumb is showing to the left side. Okay, so because of the force is pointing to the left, it will be deflected in in the in the projectile motion. It's not projectile motion. It's uh, in the half circular motion. Okay, it's circular. Actually, it's circular motion. After that, it will be going in this way. Okay. Okay. So this one will be the answer. So B pointing in. Q is will be in the circular motion. Actually, after that. Okay. And deflected. And then the force will be pointing towards the left. Okay. So question number two. For the question number two, what is the radius of the alpha particle path? So the radius we can combine into two. We have two kind of forces. One is forces by the magnetic field. Forces by magnetic field is Fb equals to uh, QVB. Depends on the charge, depends on the velocity, and depends on the how magnitude, how big is the magnitude, the strong or the magnitude of the magnetic field. And F centrifugal force Fc is have you remember remind yourself you learn in the SEM 1 is mv square over r. Okay, so we have here we combine both of them because both of them are equal. Fb equals to Fc, so qvb equals to mv square over r. Okay, so the radius we can get the, the the length of the radius from the r here. So r equals to mv oh yeah, we one more thing, you can cancel v over here. So mv divided by qv. Okay, so just substitute everything. The mass will be 4 times what is it, 4 times 1.66, 1.66 times 10 power of negative 27. Okay, it's already given, but you have to times 4 because it has 4u. Okay, and times with 7 times 10 power of 6 divided by q, that is 2 times 1.60 times 10 power negative 19, because it's 2 times 2q actually, and one more is 1.0. B is 1.0, so answer will be 0.145 meter. So the distance, the radius over here is 0.145 meter. Okay. So question number three, the speed of the alpha particle is constant. Why? The speed will be constant throughout throughout the the movement is uh, because the magnetic field, the B, Okay, the magnetic force we call as FB. Okay, acts perpendicularly to the velocity of the alpha particle. Okay, particle. Therefore, remain speed remain same. Okay, so the speed will be same throughout the motion, unless we change the angle between the velocity and the 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 between the velocity and the magnetic field flux. Okay, then will be a changing of speed. So it will be actually what happened is this alpha particle will be uh, moving in a spiral actually. Okay, in its real world, it will be moving in spiral shape. Okay, next question number 20. Okay, still the laws of electromagnetic induction and write the equation to present them. There are two laws. Okay, one is a what we call the Lenz law, or Faraday's law first. Okay, Faraday's law. It says that when the magnetic flux linkage through a circuit change, okay, and EMF which is directly proportional to the rate of change uh, of flux linkage uh, is in use. Okay. Uh, Second one, we have a Lenz law. Lenz law is the direction of the induced current is such as uh, to oppose the change which give rise to it. Okay, so Faraday's law is basically it says that when we have a change of magnetic flux, okay, such as solenoid, we put a magnetic field goes into the solenoid and we take out the magnetic bar from going in and out from the solenoid. There will be a change of magnetic flux, so there will be a induced current inside the solenoid. The Lenz law says that it's a direction. Where is the direction of the magnetic field? When we put a magnetic bar, one mouth of the solenoid will be having north or south depending uh, on the magnetic bar, the side of the magnetic bar that enters the solenoid. Okay, so that will be the Faraday's law and Lenz law. So EMF, use EMF E. Okay, so it will be d flux over dt, and where phi over here is magnetic flux linkage. Okay, now we done already number one with 3 marks. B, a metal rod PQ is moved by a force F to the right with a constant velocity V along the two parallel smooth horizontal materials for magnetic field. So this one is actually a rail. Yeah, two rails over here. two rails over here on top, and it's connected to a resistor, and we have second rail on the bottom, and the distance between the rails is divided by d, and this or the whole thing is inside the magnetic field. Okay, so magnetic field is pointing into the screen. What happens is there will be a force that's pulling this uh, metal rod, pushing to the right side. Okay, pushing the right side. One thing that is happening here is the area of the magnetic field will be increased. Okay, it will be increased. So when we have, remember, flux equals to B times A. So A is changing. Okay, A is changing in this situation. So A actually at this side. This is the A. So after, because of the A is changing, we have an induced current that flows inside the circuit. Okay. So number one, right? An expression for the magnitude of induced EMF across the metal rod. Okay. So induced EMF 1 E equals to B dV. Okay, you can check back my slide. Okay, before we have learned that E equals to E dV. So number two explain why the speed of the rod PQ is constant although it's moved by a force F. Hence, write down the expression of induced current I in the circuit of FP QG. State the direction of the induced current. Okay, number two, when the induced current, okay, flows into the rod, okay, in the rod, it's in the rod, into the rod, a force, okay, acts on the conductor, okay, in the opposite, okay, to the applied force F. Okay, so it means that when you pull over here, the F, by the Lenz's law, there will be force that is on the left side. There will be opposing. Lenz's law, it says that there will be a force that's opposed to change of give rise to it. So he doesn't want A to be increased, so there will be a force that is pushing back to the left side. So induced current equals to B dV divided by ID. Okay, and we have to clean up this one. Okay, so I equals to B dV divided by R. So F over ID, okay, times VD, because F equals to I times D. Okay, this is I times D dV over R. So you have FV divided by IR. Okay, so I will be equals to square root of FV divided by R. So it will be 2.1. The force is 2.1. Okay, and 1.5 divided by 10. Oh, this is question number 3. Forgot to tell you. This is question number 3. So it will be 0.561 ampere. Okay. The direction of induced current. The direction of induced current. Uh, current is left. left hand rule. Okay, so for force will be pointing to the left, B pointing inside. So you have a left hand rule. So force pointing to the left, B is pointing inside, so current will be pointing from Q to P. So the current will be going to flow, induced current, it's not it is induced current, it's pointing above, pointing on top to P and goes to Q, F to G and to Q. So a current will be flows in Q, P, F and G. Okay, so we continue with numbers with C. You see, for the same setup shown above, P rho PQ is now with move with the force F prime. This force makes a PQ from rest and it causes its accelerate uniformly. Reduce the equation for the magnitude to uh, of the magnitude to induce of the induced EMF in the rod PQ at the time t. So we have a force, okay, as a in accelerate. That's okay. C. So F prime minus F, okay, equals to ma because it accelerates. The force, the new force that we use is accelerating. Okay, so A will be equals to F prime minus F divided by m, and V equals to use the linear equation law. Okay, V equals to U plus AT and equals to 0 uh, plus F prime minus F divided by m and T. Okay, so V equals to uh, 0, yeah, equals to 0. So V equals to F prime minus F divided by mt. So E used by E equals to B dV equals to BD in the bracket F prime minus F divided by m and times to T. So you have, oh, this one will be the answer. Okay, so BE equals to BD F prime minus F divided by m times T. So D, an aeroplane flies north with a constant speed of 110 meter per second at constant altitude. When it's flying with its wings back at the angle of the to the horizontal, EMF induced between the wingtip is 18 millivolt. If the wingspan of the aeroplane is 20 meter, what is the vertical amount of component of the Earth magnetic field? Okay, so we have a aeroplane. Okay, wing. It was moving in 110 meter per second. Uh, and it was bunkered at angle. So the horizontal and the horizontal of the Earth. Okay, so this horizontal of the Earth will be uh, 20 degrees. Is it on this side? 20 degrees to the horizontal. MF induced between the wingtips is from here is 180 millivolts. If the span of the aeroplane is 20 meter, what is the vertical component of the Earth magnetic field? So we have here D from answer D. E equals to B and L cos theta V, B dV. Okay, because we have an angle between the horizontal and the wing. So B will be equals to E divided by L cos theta and times V. So if you substitute E, substitute everything, you have B equals to 8.71 times 10 power of negative 5 Tesla. Okay, so the Earth magnetic field component B magnetic field of the Earth is 8.71 times 10 power of negative 5 Tesla. Okay, any question? We're going to stop at here because we already running out of the question. at the end of the paper. Any question? Keshika, Yukin, and Jahan. Keshika, what happened to others? What happened to Isha and the others? How many people came? Okay, so we have Jahan, Keshika, and Yukin only in the class. So, no question. Okay, so tomorrow, is there any class tomorrow? We have a class tomorrow or not? Do we have a class tomorrow? Okay, so you have to check. I'm going to release a fourth paper, fourth model test paper, maybe tonight or tomorrow. Okay, so you should try out by yourself. I think we have done like three papers done, so I think you can try for yourself. This one is maybe easier for you, right? Okay, no class tomorrow. Okay, so no class tomorrow, and we see you on tomorrow. Will be Tuesday, and see you on Friday. Okay, see you on Friday. See you all.